Okay, so this is the second lecture on recurrent neural networks and language modeling. So last time I introduced this idea of language modeling, the basic problem of assigning probabilities to strings, sentences, or utterances in the language, with the aim of being able to compare different hypotheses from models, to be able to generate them, and in general to be able to summarize or compress histories, preserving the information that we're most interested in. So the first approach used the n-gram approximation, where we said we're just going to approximate the sort of infinite history that we may have seen with the previous n-1 words. We generalized that a little bit using neural networks so we could start to capture some correlations between the words that we've observed, the histories we'd observed, which improves things, but still it's a very rough approximation of our history to just look at the previous n-1 words. And we ended the last lecture looking at recurrent neural networks, which did away with that n-gram approximation and said instead of just cutting off the last part of the history to represent it, we're going to try and compress the whole of the history into our fixed hidden layer. And we looked at how we can do that using a recurrent network and how we can train such models by viewing them as one big network once we unfold them across time. So the aim of doing that, from moving towards these n-grams to recurrent networks, is mainly that we want to capture these long-range correlations. We believe that something in the past, beyond what we might cut off in our n-gram model, is informative to predict the next word. So in a conceptual sense, recurrent networks allow us to do that. But there's a key question of, do they actually learn those dependencies? So we're going to start this lecture with this question of how would a recurrent network actually learn these dependencies, and how can we help it do it a bit better? So here's an example of the sort of thing I'm talking about. This was the example I used last time of Alice going to the beach. And you can see that to accurately predict the next word, sandcastle, the model really needs to have some idea of what's going on in the sentence and resolve some of these dependencies. And if we have a small n-gram order, even of 4 or 5 words, it's unlikely that we'll get the right prediction. So at the bottom, we've got a sort of unrolled network where I've just shown the last output. And if we think about this long path of gradients that's going to be going from that word that we're trying to predict all the way back through our history to see how those hidden layers, the inputs back in the past, impact on that cost function. And so to capture dependencies, we're going to need to be able to follow those red gradient lines and discover strong correlations. So if we get more explicit about this, we're interested in how the gradient propagates back in time in a simple recurrent network. So I've just written here at the top, again, the standard recurrence equations for the RNN and the output equation. Sorry, that PN there, output equation, is missing a softmax function around it. There should be a softmax nonlinearity around it. But we're just focusing on HN for the moment. So at the bottom there, if we've got 4 time steps, this is what the partial derivatives look like that we're calculating in our back propagation step. So we're calculating this partial derivative. The change in the cost output at time step 4, and how a change in the hidden layer at time step 1 impacts upon that. And you can see that, except for a few terms at the start there, we get these terms which are just repeated partial derivatives for each time step we go back. And so the more time steps we go back, the more of those terms we're going to get. So let's generalize a bit and go beyond 4 time steps and just think in the limit of a long sequence of length capital N there, we're going to end up with this product at the bottom. So again, there's those first few partial derivative terms, and then we're going to get a long product of these partial derivatives of the hidden layer at time step n with respect to the hidden layer at time step n-1. So this is the key sort of formalization of this problem of we're interested in how these gradients behave, how these partial derivatives behave. And if I change that hidden layer at time step 1, is the cost function at time step capital N going to notice? Or is that just going to disappear in that long chain? Okay, so we're going to do a little bit of maths just to get some intuition here for what's happening with these gradients as we go back in time. So on the top left here, we've just got our standard recurrent network equation, and then we've got that gradient, that partial derivative with the product on the right. I'm just going to rewrite that slightly to make our lives a bit easier. So what I've done is I've expanded out V. Previously, I just referred to the import and hidden layer being concatenated and multiplied by a bid matrix V. Let's just expand those out into 2 separate linear transformations, which will be handy in a moment. And let's call everything inside the nonlinearity function G. So remember, G is our nonlinearity. It could be a sigmoid or a tan H or a rectified nonlinearity or something like that. So its argument we're going to call Zn. And thus we can update our partial derivatives on the right here just to be del Hn, del Zn, del Zn, del Hn minus 1. So we're just going to expand that slightly. So a little bit more, let's consider what those 2 partial derivatives are. The one on the left is the hidden layer with respect to Zn, the argument of the nonlinearity. And that's just the diagonal vector along the diagonal of the nonlinearity's Jacobian, its derivative. And then the second partial derivative is Zn with respect to the previous hidden layer n minus 1. And you can see if we differentiate Zn, because it's just a big linear equation, the result of that's just going to be that matrix V. That's why I expanded them out, so that we could just see that the thing that we're multiplying by the previous hidden layer is what's going to come out in the partial derivative. So this is a key thing here. Keep your eye on that. We've just remember V is a big matrix of dimension, the hidden layer squared. So when you put those 2 together, we get this term here, the diagonal of the gradient of the nonlinearity times the matrix V. And that's what's going to go in here, highlighted in red, in that product. So just a little bit of maths to rewrite those partial derivatives on the top right. And we're going to substitute those in and see what happens. So when we substitute them in, we end up with this. And the key thing that we want to look at now is that we have this matrix V inside, this linear transformation inside that product. And so hopefully if you can remember your linear algebra courses, what happens when you multiply a matrix by itself multiple times, and if you keep doing this repeatedly. And you can tell what happens by looking at the spectrum of the matrix. So if its largest eigenvalue equals 1, then that will be stable, which is nice. If it's greater than 1, this is going to explode. The numbers are going to go to infinity as you multiply more and more times. And if it's less than 1, it's going to shrink to 0. And we call these 2 cases exploding gradients or vanishing gradients. So we've got these 3 possible options that's going to happen with this recurrent network as we go further and further back in time. And the 2 bottom ones are the ones we're going to be really concerned about. We really would like the gradient to propagate nice and linearly. But it's more likely that it's going to be one of those bottom 2. It's either going to explode or it's going to disappear. If it explodes, then we're not going to be able to train our model because we're going to get infinite gradients. If it vanishes, it means that we're not going to learn long-range dependencies because we're going to have 0 gradients after a few steps back in time. So H1 is not going to influence something far in the future. So in practice, the case we mostly get is the vanishing gradient. So if we get an exploding gradient, we can deal with it relatively easily just by clipping the gradients and saying, if the gradient gets too big, let's just cut it off at a value. And that's a hyperparameter that you might put into your model. That's relatively easy to deal with. The more frustrating thing is the vanishing gradient, because if the gradient disappears or gets too small such that your machine can't represent it, then it's simply not going to influence, the outputs are not going to be influenced by things far in the past, and you're not going to learn these dependencies. So you might as well have used an n-gram model. So this can also be exacerbated by the nonlinearity. So remember, there was also the factor from the nonlinearity in that equation, which the previous few comments I've just been ignoring. But say we have a nonlinearity like a sigmoid or a tan H. So on the right here, I've drawn a sigmoid, and you see in the top right here at this part of the sigmoid, or the bottom left, the gradient of that function approaches 0. Same for the tan H, obviously. So if you end up in either of those regimes, then that extra term that you're multiplying with is also going to be small, and it's also going to approach 0. And so your gradients are going to vanish even more quickly. So all of these things are bad. So, and this is the key problem with simple recurrent neural networks, and why, if you just take what I described in the previous lecture, the simple recurrent neural network, ordinary stochastic gradient descent, and try and train a model, it probably won't be terribly effective. Maybe a little bit more effective than an n-gram model, but there won't be a huge difference. It won't be capturing really long-range dependencies. So this is a key problem to overcome. So there's lots of ways of approaching this. One, you could view this from an optimization point of view and say the problem here is that we're doing first-order gradient descent. We're only looking at the first derivatives. If we looked at the second derivatives, if we looked at the curvature of the function, then we wouldn't have this problem. Now, ideally that makes sense. The problem is it's very hard to do second-order gradient descents on the sorts of size of models that we're interested in deep learning. Second-order methods are often referred to as Newtonian methods, and you can approximate those, and those are often referred to as quasi-Newtonian methods. Popular ones are things like LBFGS and such things you might come across. These can work, but none of them are terribly popular on the sorts of large-scale problems we'd like to work on. Another approach is very careful initialization to try and get yourself in that regime where the gradients propagate, where I said if the eigenvalues are, the greatest eigenvalue is 1. If you can get your model to start with in that area with a careful initialization, you might get nice long-range propagation of your gradients. And there's quite a bit of work. You can find a number of papers, and there's a blog post I referenced at the bottom there, which go into this idea of what's the optimal way to initialize one of these models. But by far the most popular way of approaching this problem is just to change the architecture of the model. So to say the problem, that the optimization problem's too hard, so instead let's change the model to try and force gradients to propagate more easily. And so I'll try and sort of walk you through this idea and introduce you to something called the long short-term memory, or the LSTM. And this is, along with maybe convolution networks in vision, one of the two biggest innovations which has led to a lot of the interest in deep learning recently. LSTMs, just like convolution networks, actually go back a long way to the 90s, but it's only recently that they've really become popular and scaled to lots of compelling problems. So we're going to step through starting at our simple recurrent network and gradually making it more and more complicated until we end up with what's quite a mess at the end. But hopefully you might follow the intuition here for what we're trying to do. So this is our simple network. I've just stretched things out a bit to leave room for what's going to come. So we have two time steps, hn-1 and hn, and we're interested in how the hidden layer at the previous time step gets updated to the next time step. Our update equation is at the top there. So the first thing I'm going to do is just be a bit more explicit. In all my diagrams, I've been quite loose in just drawing these arrows, but of course, those arrows correspond to linear transformations and nonlinear layers and things like that. So I'm just going to draw one of those on explicitly. So now I've drawn on that when we go from hn-1 to hn, we're going to pass hn-1 and the input wn-1 through linear transformation, then a tan h nonlinearity. So I'm just going to draw that on explicitly, because I'm going to start drawing more and more of these on this graph. So that's my drawing of our simple recurrent neural network. The next step I'm going to do is introduce an extra layer here called the cell state C. And we're going to think of this as our memory. And we're just going to promote the hidden layer up a layer there. And if you look at the equation at the top, we're going to update the cell state by taking the previous cell state and then adding in a contribution from our hidden layer and our input, which looks just like what we had previously in the simple recurrent network. The difference now is that the core recurrent backbone of this network is the updates to the cell state. And the really core thing is that these updates are additive. So this is a plus. In the simple recurrent network, as we went from one hidden layer to the next, we were multiplying. So the backbone of the network was lots of multiplications. Now in this case, I've changed this to be additive. So now we're adding. And if you think about what happens when you differentiate the sum rather than the product, is that you get essentially an identity. So gradient flows really rather nicely back through the sum. So this is the key innovation. There's going to be lots more additions to come, but the key thing you should keep in your mind when thinking about LSTMs, abstracting away all the complications, is this replacing the multiplication with a sum. That's what it's all about. And all of the extra complications are just making that work. Because the problem we have with just introducing the sum is now we're just taking the cell state C and we're adding something to it at every time step. And you can imagine that this might get unbalanced or just grow and grow and grow or something like that. So we're going to have to worry about how should we balance these two terms in our update. But keep coming back to that key idea that we're just replacing multiplication with addition. So that's our first step. We now have previous cell state plus update from the previous hidden layer and the input. So the next thing we're going to do is something called gating. So we're going to gate the contribution from the input in the previous hidden layer. Now, and we're going to call this the input gate, represented by I there. The idea of gating in neural networks is just computing a nonlinearity which is bounded between 0 and 1, and we think of that like a switch. If it's 1, we're turning on a connection. If it's 0, we're shutting off a connection. The key thing is this is not actually a discrete binary function. It is a continuous function, so that we can differentiate it later on and we can do backpropagation. But in your intuition, you can think of it like a binary switch. So at the bottom, we're going to introduce this gate. And you see the sigmoid function there, of course, is bounded between 0 and 1. And so we're going to take a new linear transformation of the input in the previous hidden layer. We're going to apply a sigmoid to it, and we're going to get a vector of gates. And in my little diagram there, you see that input IN, that input gate, is going to get multiplied by the contribution from the tan H. And what this is going to do is, you think if that gate is 1, then we're going to get a big contribution from the current input. If that gate is 0, we're going to get no contribution from the current input. So it gives the model the ability to ignore inputs and just propagate. So if it's 0, then the cell state at n is equal to the cell state at n minus 1. So there's been no update. So gradient propagates perfectly, and the model forgets nothing. So if a gate is closed for many time steps, it's almost as if those time steps didn't happen, and you can get very long-range dependencies propagating through them. Also remember that IN is a vector, as is the output of tan H. So we have a different gate for every hidden unit. So some hidden units can be on at a time step, and some hidden units can be off. So we can imagine hidden units that just detect particular things, like they might be on whenever there's a noun, and they might be gated off whenever there's something that's not a noun. You also might imagine something like a full stop, the end of a sentence, shutting down a lot of the gates. Okay, we're still a bit unbalanced because now we have the ability to either include or ignore what's coming into the input, but we don't have the ability to forget things that are in our cell state. So that's our next addition to the model. So next we're going to add what we call the forget gate. And exactly the same as the input gate, this is a sigmoid function of a new linear function of the input in the hidden layer. And we multiply the previous cell state by this forget gate. And so now this is really most of our LSTM. So now we're saying that our new memory, our new cell state, is some mixture of the previous cell state weighted by the forget gate and our new update from our input and the previous hidden layer weighted by the input gate. So now with INF, the model can choose at every given time step for each unit in the model, in the hidden layer, how much should I just copy across the previous memory and how much should I change it given my current input. If the forget gate is set to 0, then, and imagine all of the forget gates set to 0, then that's equivalent to just forgetting all of the memory at that point and starting afresh. As is, if the input gate is set to 0, that's equivalent to just ignoring the input. So now the model really is able to choose between, do I just propagate information forward perfectly and ignore inputs in a unit, or do I forget what I've seen and introduce something new? So this is the core of the LSTM. There's one final addition, mostly just because we can. Once we've started doing all this gating, we think, why not put a gate on the output as well? So you'll see in LSTMs most of the time they'll have a gate on the output from the cell state to the hidden layer. And this allows the model to essentially choose what it exposes at any time step to another network reading from it. So if this gate zeroes out some of the dimensions, it's essentially saying that these dimensions are not visible to whatever's reading that hidden state. Yep. So the tan-h, you have some choice about whether you use the tan-h there. You could use other functions. With the sigmoid, you really want to use a sigmoid because you want something bounded between 0 and 1. It doesn't really make sense to use a tan-h there and have sort of negative gating. So if you think of the gate as essentially a 0 or 1 variable, the sigmoid is a nice function for that because it gives you a continuous 0 or 1. So yes, sigmoids are really a logical choice for gates. The tan-h, you could replace that with a rectified nonlinearity or some other nonlinearity of your choice. Almost always in LSTMs, people use tan-h's and they do seem to behave quite well. Andrew?
What's the intuition for the functionality that occurs in the hidden layer versus the cell state? Like what's supposed to be happening in the cell state is not happening in the hidden layer, vice versa?
So the cell state is sort of your nice, clean, unadulterated memory because it's nice and linear and you're not doing anything nonlinear to it. Every time you do anything nonlinear, like apply a tan-h or multiply it by something, you're going to get gradient shrinking. So you really want that backbone of a nice cell state that's not going through nonlinearities if it can choose to. So it can choose to set the forget gate to 0, set the input gate to 1, and everything just propagates perfectly. The intuition between having the hidden layer is just sort of the standard deep network intuition that we want to be able to calculate complex functions of that cell state. So the reason the hidden layer is going into that input, the input up here is, and all of these gates, is to make them all dependent on the past. So you can make your gating decisions dependent on what you've seen in the past. And that's gone through, it'll go through sort of 1 or 2 nonlinearities, and that gives you a bit more sort of functional power. But in a couple more slides, I'll show an alternative to this that does that slightly differently. Okay, so that's the LSTM. As I keep repeating, the key thing here is the choice to add rather than multiply. So I've also included here a diagram that I've stolen from Christopher Oller's blog, which is a nice blog to read about these models, because it's just a really nice way of diagramming these models, LSTMs. So I'll also show that. And the key thing to notice in this diagram is this straight line here, and that's our cell state C, and you think of that nice straight line as showing that gradient can just propagate along that for as long as it wants, only interrupted by this multiplication and this addition. So this multiplication is the forget gate. So if that's set to 1, that's like it not being there. And this addition is where the input influence comes in, modulated by an input gate. And we also have our output gate over here. But this is also a nice and admittedly cleaner than my diagram representation of the LSTM. So just for being complete, I've put all of the equations of the LSTM in the slides here. I've just separated out the cell state input update into a sort of cell state hat there. But these are the equations from the previous slide. Now, if you go to try and implement this, one, there's quite a few things to calculate now. You'll notice with your simple recurrent network, it was quite simple. You just had take the previous hidden layer, apply a linear transformation to it, you get the new one. Yeah.
Sorry, what does the circle mean?
Oh, sorry, that's just element-wise multiplication.
Okay.
So those are two vectors, and we're saying just multiply them element-wise. So not a dot product.
Okay. To give a vector.
To give a new vector of the same dimension. So for instance, the forget gate and the previous cell state have the same dimension, and you want each one of the forget gate cells, which are our 0 or 1 variables, to multiply across to the corresponding dimension in the cell state. So from an implementation point of view, this looks ugly, but of course, with toolkits like Torch or TensorFlow or things like that, it's very easy to write out these equations and have the toolkit calculate them for you. One thing to note is you don't actually want to do all of these calculations independently. You'll notice that you're doing lots of linear transformations here, all of these linear transformations on the same inputs. So really what you should do is put that into one big linear transformation. So concatenate those linear transformations together and pass your previous word and your previous hidden state through them. There's a number of other implementation efficiencies you can get by rearranging these a little bit. You'll find those in the reference at the bottom there to how we can optimize these networks in implementation, and a description of how it's done in the NVIDIA toolkit. There's also a citation there to the original LSTM paper from Hochreiter and Schmidt-Huber from, as I said, this goes back to the 90s. But was really popularized in the sort of later 2000s by Alex Graves, again working with Schmidt-Huber. But for a long time, even though back in the, almost 20 years ago, these guys had demonstrated that these models could learn very long-range dependencies, no one really picked up on it until about 10 years later. So that's the LSTM. And as I said, that's really one of the core contributions in deep learning. Okay. One I forgot, but before I move on, a very common variant that you'll see of the LSTM is to get rid of the input gate and just have one gate, the forget gate, and make the input gate 1 minus that. And that sort of makes sense. It sort of says, if I want to completely forget, then I will take all of the input. If I want to completely remember, and then I'll take none of the input, and then we can have a mixture between the two. So that's a very common modification. Yep. So C is the cell state, Cn, and the C hat is just a notational convenience, so I could put that equation on the lower line. Yeah.
So is it equivalent to anything we've seen before?
So the way you can think of it like that, it is the recurrent hidden state, but we use a different name for it as such because we're not doing this multiplicative updating. So and there's no nonlinearities going through it if the gates are arranged in the right way. So we use this different name as a sort of cell state, but you can think of it as the new version of the hidden layer. Okay. I thought I'd throw this in for completeness. Another popular variant of this that's been used a lot more recently is something called the GRU, or gated recurrent unit. Here's, again, Christopher Olar's nice diagram of this. And this gets rid of a few of the features of the LSTM with the intention of making it a bit simpler, a bit more streamlined, and maybe a bit faster on modern hardware. Whether it is actually any faster in an optimized implementation is not clear. But you can see now, rather than having a C and a cell state and a hidden H being propagated at each time step, we just keep the H. Again, we have this backbone that's just interrupted by a gate and an addition. But this time we sort of reuse the H for double duty, where we had two separate things in the LSTM. But that's another variant. And again, there are the equations introduced a couple of years ago in the context of neural machine translation. Okay, so that was I think the most popular solution to this vanishing gradient problem. It doesn't completely solve the vanishing gradient problem. We still have plenty of nonlinearities. And we still have the problem that if dependencies are very long in the past and there's lots of other noise going on, they're still quite hard to discover. But these these networks do really make it easier to find long-range dependencies without lots of careful initialization and fiddling and such things. So that's what I mean when I say they just work. So now the LSTM is really the go-to recurrent model. If anyone's wanting to model a sequence these days, the first thing they do is throw an LSTM at it. And often that will just work. And this has been a key innovation in lots of the models which have got people excited about deep learning. So the neural machine translation systems, the new generation of speech recognition and text-to-speech systems. These are almost all using LSTM backbones. One of the downsides of these models is they're a bit more complicated. They have more parameters as such, and lots of those parameters aren't actually in the memory. So you've got all these extra parameters for the gates that aren't going into the memory. So you've increased the size of the model, but you get less memory for the absolute number of parameters. There's a really nice recent paper from the last few months that does look at lots of these different architectures and compares them explicitly on the number of parameters versus the memory and performance, and finds that most of the time the architecture is less important than just the sheer number of parameters. But the architecture definitely impacts on learnability, which is this problem of finding the dependencies. Okay, so that was LSTMs and gated recurrent units. So we're going to move on now to the next topic, which is depth. So obviously this course is called Deep NLP, so we should have deep networks. Now any recurrent network you can see as a deep neural network. If you think about the unrolled network and you take from the first time step to the last one, the information is going through lots of nonlinearities. But at the same time, if you think of any one time step, they might look not so deep because the path from the input to the output is only going through one nonlinearity. So we can also make our recurrent networks deep. What we mean by a deep recurrent network is slightly ambiguous. You have a few different choices of how you make these models deep. The most popular option in that you see is to make them deep in the sort of vertical dimension here. So like this. So we can add extra layers of network, and we can feed the hidden layer of one network, one recurrent layer, into the input of the next one. And we can do this as much as we want. Now, if you think of what this buys us, so as I sort of say at the top there, if we just have one layer of recurrent network and we want more memory, we can increase the hidden layer's size, but the size of the recurrent transformation increases quadratically, because of course it's the square of the size of the hidden layer. And that's bad, because as you go from, say, 1,000 units to 10,000 units, you're going to go from 1 million parameters to 100 million parameters. And so that's not ideal growth. So that's going to get computationally heavy and take up lots of your GPU's memory quite quickly. So a different way of getting more memory is just to have multiple hidden layers, and you get that from depth. You can think of each one of these recurrent layers here as an element of the memory. But you have a separate linear transformation for each one. So each time you add another layer, there's only really a linear cost. So that's a way of getting more memory with a linear cost rather than a quadratic cost. You also get deeper computations, which we all love in deep learning. So now the path from the input to the output is going through multiple nonlinearities. So you might hope that it learns more general functions. An implementation trick or tip is that while deep networks are great, it is often quite hard to get gradients to propagate through deep networks, as we have just discussed with recurrent networks. So a good idea is to include something like skip connections. So my little arrows here mean that it's not a bad idea to just have bypassing connections from each layer to the output so that you get nice linear paths for the gradient to flow through. It makes learning much quicker. Okay, so another option is to make our networks wider rather than deeper in the vertical. So we can think of this as deep in time. So here's our standard recurrent network. And then we can just add extra steps in for each one of our real steps. So for each real time step T1, T2, we can add sort of T11, T12, T21, T22. So we get these extra steps. And now you can see that the path again from the input to the output is deep in the sense that it's going through multiple nonlinear layers. But in a different way to if we have depth in the vertical. Now, you can also see that this is not increasing our memory because we still have one recurrent sequence. But it is increasing our representational efficiency, hopefully. This idea has recently been used quite effectively in something called the recurrent highway network, which is essentially just this sort of architecture where the recurrent units are things that look very much like the GRU units that I showed you. It also has some skip connections and some other features, but it's wide in time. So these are your different options for depth. And of course you can combine them. You can add extra layers of this sort of network to get deep in both the vertical and in time. The real limitation is how much computation you have and how much memory you have to store all of the weights in these models. Okay, so that's depth. So another issue we're going to move on to is efficiency in terms of the softmax output. And this is a particular issue in language modeling with recurrent networks. So if we're doing language modeling and we're doing it at the word level, we have a vocabulary. And as I've said, vocabularies are normally big if you look at real text. So if you gather lots of text off the web in English, the vocabulary will grow quite quickly. And if you want to do something like machine translation or speech recognition, you really want to keep around hundreds of thousands of words, maybe millions in your vocabulary. If you restrict them, if you think, well, there really aren't that many words in English, we can just keep 10,000, you'll find that's not actually true. There are a lot of words. If you go to morphologically rich languages, something more interesting than English, then that grows much more quickly. Classic examples being Turkish or Finnish or something like that, where the vocabulary grows extremely quickly. And so your softmax layer is going to be big. And this is an efficiency problem because if at every time step you have to do a vector matrix product with a million times whatever your word representation size is, maybe 1024 or something like that, that's going to take a little bit of time. GPUs can make this fast, but even GPUs have their limits. Normally at the vocabulary of the tens of thousands, it will start to get really quite slow. So we want to do this faster, especially at training time. Well, really at test time as well. So the key thing is our linear transformation here. So WHN. So there's lots of different approaches to speeding this up, but I'll try and break them down into a few categories. There's obvious ideas like, one idea is shortlists. And this is sort of the simplest heuristic, which is just say, let's use our recurrent neural network to get probabilities for the first, 10,000 words, the most frequent 10,000 words. And then for everything less frequent than that, let's use an n-gram model or some other simpler model that's faster and doesn't slow down with big vocabularies. That's an easy thing to do, but given that one of the advantages of these recurrent models is that they can capture correlations between words in the vocabulary and thus get good probabilities for words they don't see very often. That is, they might have seen a particular word like run many times, but they've never seen it inflected as running. But they know but the model knows what happens when you do that, so it can predict nicely what the probability for that word should be. So you don't want to get rid of the rare words because that's where a lot of the gain of your model comes from. Another idea is what I've called batch local shortlist, which is to say every time you process a batch of sequences in your model, you just use the vocabulary in that batch and you ignore any words that are not in that. And that's quite a reasonable engineering solution, often used in machine translation systems to get good speed. Again, though, it is quite a harsh approximation of the probabilities and can be a bit unstable. So another popular approach is to either approximate the the gradient of the softmax, or to change the objective function to something which is going to be quicker to compute. So what we're saying here is, what I've done here is to expand out the softmax into the bit which is on the numerator and the denominator. Remember, the denominator is a sum over the whole vocabulary. And I've just summarized that by saying it's exponentiated of some variable c. Now, in reality, c is defined as the sum over all of these numerators. But we could be tempted to just decouple them and say these are different parameters in our model and let's optimize them separately. That way we might get away with not doing that big sum. Now, we can't do that in the trivial sense because otherwise we wouldn't get a well-defined normalized probability distribution, because that's exactly what the job of that C is to do, to normalize. But if we're a bit clever about it, we can come up with some novel objective functions which leverage this. And this is what something called noise contrastive estimation does, an idea introduced by Min and Yue. And the idea there is, rather than doing what we do with a softmax, which is to say at each time step we look at the word we want to predict and the whole vocabulary, and we try and maximize the probability of the word we want to predict and minimize the probability of all the other words at every time step. Instead of doing that, what we do is we take the word we want to predict and then we sample k, what we call noise samples. And then for each one of those, both the true word and our noise samples, we make a binary prediction. And we just predict, is this a noise sample or is it the true word? So now, rather than a big softmax over the whole vocabulary, now we have a series of binary decisions. And binary decisions are very fast to calculate because you only have to consider two options. So this is what this little equation here is saying. So our model just learns to distinguish samples as either being true samples from the data or samples from our noise distribution. And it turns out that if you, in the limit of the number of samples, this will match the maximum likelihood objective. So if you take an infinite number of samples and do this optimization, you'll end up with the same objective function. And that's nice, because it's nice to be consistent. In reality, of course, we're not going to take an infinite number of samples. We might take only a few. We might take just one if we're really in a hurry. But this objective function works quite well. And this general idea has been tried in lots of different forms. Oh, one thing I should note here is that the key thing about this is we still have the same model. So these binary decisions don't give us the probability of the word actually appearing. It's just whether the word is a noise word or the real word. So at test time, when we actually do want to know the real probability, we still have to do the full softmax. So this approach doesn't make our model any faster when we want to deploy it. It makes it faster when we train it, but not when we deploy it. Now, as researchers, we care a lot about training because we're always coming up with new models and we're always training them. So we want training to be really fast, and we have small test sets. So we're not too worried about test time. In industry, of course, you train a model once, hopefully, and then you deploy it, and then it does lots of work evaluating people's speech in a speech recognizer or machine translation output. So in that case, you're less worried about how long it takes to train. If it's 1 week or 3 weeks, that's okay, but you want it to be fast when you deploy it. So when you read research papers, it's worth realizing there's often different objectives between research and industry in this respect. Okay, so another popular variant that you might see, and you've seen this paper at the bottom, which presented some large-scale language models, is something called importance sampling, which takes this binary objective and instead says, rather than classifying each sample as true data or noise, let's take our k plus 1, that is our true data, plus our k noise, and do a softmax over those. So now you're back to doing a softmax, but it's much smaller than your original softmax. So that's a different variant on this, and maybe it's a bit more stable. Okay, switching to a different idea. So those previous examples were approximating the objective function with something that's sampled, so a stochastic approximation. We can make some assumptions about the probability distribution that will also make our models faster to train. And the classic one is what we call factorizing the output softmax. So on the left, we've got this probability. We want the probability of the word that we're going to predict given the history. And normally we predict this from just a big softmax over the vocabulary. But remember, we can use the chain rule, just like we did for language modeling to decompose the joint probability into a series of conditionals. We can use the same idea to decompose that one big softmax into a series of softmaxes. So now we say, let's assume that we have a function which maps every word to a class, so an integer value. And imagine our set of classes is much smaller than our vocabulary. So our vocabulary may be a million words, and our number of classes may be 1,000. And every word belongs to one class, and that's hopefully, if we did it right, they're balanced. So we might have 1,000 words in each class in that case. And now what we're going to do is, instead of just predicting the word from the full vocabulary, we're first going to predict which class it's in, and then given the class we've predicted, we're going to predict which one of the words in that class it is. So now we're going to have two softmaxes. But if you think about them, each one's going to be smaller. So now rather than a softmax over 1,000,000 words, we have one softmax over 1,000 classes and another softmax over 1,000 words which are in that class. So this is a factorization. A two-level factorization, because we have two softmaxes there. And so this is very effective. This essentially gives us a quadratic speedup. So if we choose our classes carefully, and a good choice is, for number is a square root of the size of the vocabulary, then rather than v computations in our softmax, we're going to have 2 square root v. That's good. One problem, you have to choose how to get the classes. Thankfully, especially from the world of information retrieval, there's lots of algorithms for grouping or binning vocabularies into classes. So you can take one of these off the shelf and use them. Ones that do it based on frequency are a bad idea. People have used these in the past, but it's best to use ones that are actually based on the distribution of the words. But this is a classic factorization, and this sort of technique actually is very effective. And the nice thing is that it does give you valid probabilities. So your p on the left there is still a valid, well-normalized probability. You can take this idea further and say, well, why stop at one factorization? Why not just keep going? And you could turn this into a binary tree of decisions. And so now you have a binary tree where the leaves are the words in your vocabulary, and you predict the word by making choices about, do I go left or right at each branch in the tree? And so we can think of this as assigning a binary code to every word in the vocabulary, and then predicting each one of the bits in that binary code, given the ones we predicted so far. So this gives us an even better speed up. So now we get a log speed up, and that's quite good, because now we can have really big vocabularies without slowing down significantly. The downside of this is, firstly, it's hard to come up with a good binary tree. It's much easier to just group sets of words into classes than it is to assign them to a whole binary tree. And no one yet really has a good solution for this. The second one is binary trees, and this sort of path following approach is not so easy to optimize on a GPU. So while you do a lot less computations, you'll be doing them on the CPU rather than the GPU, which might negate some of the gain. I've also thrown in a reference at the bottom to a recent paper from the Facebook group, which look at ways of learning this sort of hierarchical factorization specifically to optimize for a GPU. So rather than using binary trees, they actually use sort of n-ary trees that are not balanced, and they specifically try and optimize for the GPU, and they get quite good results. Okay. So just a summary slide for comparing these different approaches in terms of efficiency. So as I said, there's a difference between training and evaluation at test time and sampling. So evaluation here means, given a sequence at test time, given a new utterance, I want to be able to work out what its probability is. And that boils down to, I tell you what the next word is, and I want the model to tell me what's the probability of that next word. That's what we need to do to get perplexities and things like that for testing. If we're doing something like translation, then we're not given the next word, we have to decide what the next word is. So in that case, that's what I refer to as sampling, sometimes called decoding. Then you actually want to sample from that distribution. So for each one of those options, I've given the different complexities. The key ones to note are things like the, obviously the full softmax is always the complexity of the vocabulary. Noise contrastive estimation at the bottom there speeds things up at training, but doesn't really help you at evaluation or decoding sampling time. The various factorizations speed up at both training and just evaluating probabilities, but if you need to sample from them, in the worst case, you might need to enumerate all paths in your tree or all cases in your factorization. But the average case is often much better. You can often sample from the tree very efficiently. Actually, that's slightly misleading. You can sample from the tree in linear time quite effectively. If you want to maximize, it's going to be worst case V. Okay, so that's slightly incorrect there. So maximizing is what I really meant by sampling there. Okay, so one more thing on vocabularies and efficiency. So a different approach is to just get rid of this big softmax over words by looking at some smaller unit. And the obvious one is characters. So there's a lot less characters than there are words. So why not just train our recurrent model on the character stream rather than thinking of it as a sequence of words? Let's just think of it as a sequence of characters. Obviously, we then have to include the space as an output. But this is a relatively natural way of re-representing the data. It's also natural because that's the way the data comes to us. It doesn't come tokenized nicely into words, and in lots of languages, splitting the input up into nice word-like units is hard, especially non-segmenting languages like Mandarin. If you're a Mandarin speaker, you know that it doesn't come written nicely segmented into words. It's not even clear how to segment it into words. So the idea of just dealing with characters is compelling. And this gets rid of really your softmax problem, because now your output space may be a few hundred or less. That's relatively small, and that's going to become largely irrelevant for your computation, and now you're just going to be worried about your recurrent layer. But there are downsides. Obviously, there's a lot more characters in a string than there are words, so your sequence is going to get a lot longer. This issue with backpropagating gradients is going to get worse because all the paths are longer. Also, a lot of the structure in language at the bottom level is in the words. And we want to learn correlations between the words. But the model doesn't get the whole words as a unit, it gets the characters. So it now has to learn what a word is. It has to learn that DOG refers to dog, and then it can correlate it with some other sequence of characters. So you've made the learning problem for the model harder and more nonlinear. But from a sort of obsessive modeling point of view, this seems like the right way to do it. So if we can work out how to model characters in these recurrent models efficiently, that would solve lots of our problems. It would also solve the problems that we never have this issue of unknown words. So one of the problems if we have a fixed vocabulary is someone gives us a sentence and asks us what the probability is, and it has a name in there like go back maybe, how long do we have to go back? About 15 years, and it's very unlikely you would have seen the name Barack Obama in text very often. Go forward a few years and suddenly it's everywhere. Now, if that's not in your vocabulary, you have no way of assigning a probability to it. The nice thing about using characters is you can assign a probability to any sequence of characters, even if you've never seen that word before. You can also discover correlations in the character representations of words, the orthography. So my examples there, as limited as English morphology is, there is still a bit. So disunited, disinherited, disinterested. We can see that these all share a similar series of inflections, and if the model has never seen one of these before but has seen the others a lot, it can guess what sort of context that new word might occur in. But if all it has is a vocabulary index for that word, it doesn't get that information. Okay, how are we going for time? Okay, so another topic in this lecture is regularization. So this hasn't come up yet, but a key problem with anything in machine learning is how do we ensure our model generalizes? How do we stop it just fitting the training data perfectly, but never generalizing to anything new? And so this is a problem of regularization. In the world of deep learning, by far the most popular way of regularizing deep models is something called dropout. Hopefully you've seen this in the past in sort of introduction to machine learning. But if not, the idea behind dropout is very simple. Basically, for all the hidden layers in your network, you sample a bit mask, ones and zeros, for that hidden layer, and you multiply this randomly sampled bit mask by the hidden layer, essentially dropping out certain units. And you do that as you're forward propagating, and then when you back propagate, no gradient goes through those dropped out units. And this has the effect of making the model not rely on any particular unit being there. It has to be robust to units disappearing. And this makes the functions that learn a bit more robust and not overfit the data, not hone in on very specific properties of the data to predict the outputs rather than general properties. Now, we'd like to use this in recurrent networks, but it turns out that if you just use a straightforward application of dropout to recurrent networks, it doesn't work. So why it doesn't work is because, so when I say applying it to recurrent networks, I mean applying it to the recurrent connections here, so between the hidden layers. And why it doesn't work is if you randomly sample a mask at each time step and multiply the recurrent hidden layer by that, after a certain number of time steps, a very popular parameter for dropout is 0.5, so that's 0.5 probability of a 1 or 0.5 probability of a 0. So equal probability of a unit being dropped or being kept. Now if you do that a couple of times, in expectation, every hidden unit is going to get dropped after a few time steps. So that means that gradient is never going to propagate more than a couple of time steps back in time, because it's always going to hit a dropped out unit and stop doing anything useful. So just applying dropout in a basic fashion between recurrent units, recurrent layers, is a bad idea and doesn't really work. The easy solution to that is just not to do it and to put dropout everywhere else in the network. And this is basically the approach advocated by Wojciech Zarumba in the reference I give at the bottom there. So my little dropout boxes there show that we can apply dropout when the input comes in, we can apply dropout when the output goes out, but we won't apply it through the recurrent connections. And that's pretty effective. It gets you a reasonable amount of regularization and reasonable stability in these models. And our sort of modus operandi in deep learning often is to try and train the biggest network we possibly can, even though we know it's going to overfit the data way too much, and then regularize it really heavily. This is a very common thing in deep learning, and as you over-parameterize your model. Another way of regularizing your model, of course, is just to use a model that's too small to overfit the data. But it seems much better to use one that's way too big and then regularize it heavily. Okay, so this gives us a basic form of regularization on recurrent layers, but we're still missing out because our recurrent part of the network is not really getting regularized, and that's probably bad. There's been quite a few proposals for what the best way to do this is, and you can read about those in various references. One approach that seems quite popular at the moment is something introduced by Yaron Gull, who's a PhD student at Cambridge. He was a master's student here a number of years ago. And he introduced this idea that, as very simply saying, well, rather than doing our usual thing of sampling a random mask for every connection in dropout, we're going to sample one random mask for the recurrent connections and use the same mask at every time step. So now you don't have that problem of, in expectation, a unit being dropped, because now either a unit is dropped for all time or is it kept for all time. This only works, of course, if you have multiple sequences. If you have one sequence, it's sort of pointless. But if you have lots of sentences, you can see how this will, in one sentence, it will drop out a set of units for the whole sentence. In a different sentence, it will choose a different set. So this works. Yaron has some nice theoretical justification for it. The downside is it's sort of inefficient, because for this to work, you want lots of randomness in your dropout, and now you can only sample once per sentence. So I think most of the results using this have been on pretty small data sets. Another innovation that Yaron introduced is the idea of sampling at test time as well with different dropout masks, and he has a Bayesian justification for this, which is worth reading in that paper. Okay, question.
What was the cost in the previous slide?
What was cost?
Yeah.
So cost is a standard cross-entropy cost, so just like it has been in all of the previous diagrams. So our objective function at the top is just the accumulated cross-entropy. So we don't change the, yeah.
So why are we feeding W1 to 4 from the top, but feeding W0 to W3 at the bottom?
So the cost function takes two parameters. So of course, the aim of your language model is to predict what the next word should be. And the distribution P, the vector there, P, should be a distribution over the next words. So you want to know, for cost to work out how well your model did, how in that prediction, it has to know what the true prediction was, and that's why it's got W1 coming at the top. That's the true prediction. And in P, it's going to look at what's the probability in P corresponding to W1. So what probability did the model assign to that prediction? It's going to compare those and work out what the cost is. So that's just illustrating the arguments to the function. And if you remember from my diagrams in the previous lecture, no gradient went up there. So there's no gradient going up to W1. Of course, the words at the bottom, they're the things we condition on at each time step. So for whenever we're predicting the next word, we're always conditioning on the previous one. So I said, so at each time step you have the hidden layer summarizing your history, and you have the previous word. So if it was sort of the dog, then your input would be dog, and maybe the next word that you want to predict is barked or something like that. Okay. So we're coming to the end for this lecture, and here's my big summary slide of what we've covered. So lots of different little things about recurrent networks in practice and what you need to worry about. So as we started out with long-range dependencies, we looked at this problem of exploding and vanishing gradients. I suggested some different solutions, but in particular, the solution of using gates and additive recurrences, in particular the LSTM. And so the recommendation there is if you're going to apply a recurrent neural network to something, starting with an LSTM is a pretty good idea. We looked at deep recurrent networks, ways of increasing the memory and representational efficiency of the models. That's relatively straightforward. We can go deep in depth or deep in time. These have different trade-offs. And we also looked quite a bit about how do we approximate this big vocabulary. So we looked at lots of different ways. We can sample, we can factorize it into trees. And at the end I sort of said, well, ultimately we don't want to do this. What we really want to do is just model the characters that are coming in. We've not quite solved how to do that to the same level that we can model words, but we're getting there. Okay, so here's lots of references overlapping with the ones I gave in the lecture and a few extras. Some blog posts at the bottom there. So the one I took those images from, Christopher Ohlers, one is very good for understanding LSTMs. And also there's a nice blog post from Yurin there who explains his recurrent dropout approach. And so that's it for recurrent networks this week. Next week you can come along for classification of text with deep models on Tuesday. Carl Moritz will give that lecture. And then on Thursday, Jeremy Appleyard from NVIDIA will come and talk about their GPUs and how you can optimize your models for GPUs. And yeah, ask some questions before you run away.
What is memory capacity?
What is the memory capacity? Okay, so by memory capacity I mean the hidden layer. Occasionally I may misuse it because of course you have your computer's memory and the recurrent network's memory. But we think of that recurrent hidden layer or the cell state in LSTM as its memory. Everything about the history is compressed into that vector. So it's everything it remembers about the past. So that's what I say by memory, and if we want to remember more, we're going to need a bigger vector. So if you say there's lots of things in the past I want to remember, then you might want to make that, that hidden state bigger, and as I pointed out, there's various costs to doing that at the back there.
So in all your examples, you used mainly fixed length vectors as input vectors. How do you deal with like variable length sequences?
Sorry, variable length sequences or variable length input representations?
Variable length sequences going in, not input representations.
So you can easily deal with, so the recurrent network, because the weights are tied at each time step, you can have as many time steps as you want, that's not a problem. So if you have any finite sequence, you can run your recurrent network on it, you can unroll it, you can backpropagate through it. So this is what I discussed a little bit at the end of the last lecture where we talked about backpropagation through time versus truncated backpropagation through time. You can do that in theory easily. If your sequence gets too long, you'll need to start breaking it up in order to do the computation. And so the solutions we looked at in the lecture on Tuesday were the truncating the gradients so they don't flow back, and then you can parallelize these But in practice, there's no problem with having different length sequences. There's some efficiency issues with mini batching, but yeah.
So would you pad it with zeros just very practically?
So if you have a mini batch of sequences of different lengths, then the simplest thing to do is to pad the shorter ones with some sort of zero or null marker until they're all the same length as the longest one, and then have some logic in your cost function basically to ignore those time steps, so they're not included in the cost. So that's the simplest approach. Of course, you do some wasted computation then. If you want to not do that wasted computation, you need to do some more engineering, but it's possible. And for instance, the NVIDIA recurrent network library has all of that sort of thing hidden in it under the hood. Okay, are there any more questions? Oh, one more down here.
How's the class label represented, like vocabulary? Is it one hop or binary?
So the import vocabulary, yes, will always be a one-hot representation on the input, and what's going in at the top for the cost function will also be a one-hot representation. In practice, that means it's just an index because you're not actually going to store the whole sparse vector. But the p vector on those diagrams of probability, it of course is dense, so it is a big long vector of the length of the vocabulary with a probability for each word.